On the morning of January 16, 1943, the brand-new Liberty ship SS Schenectady lay moored at the fitting-out dock of the Kaiser Shipyard in Portland, Oregon. Her trials were complete. Fuel and stores had been loaded. She was, by all appearances, ready for service. A handful of crew and yard workers were still aboard when the sound came, sharp, metallic, unmistakable. Witnesses later described it as a pistol shot magnified 1,000 times. Others said it began as a low groan, a deep vibration through the decks, followed by a clean, ringing snap. The hull opened amidships, not torn, not twisted, but split almost exactly along its transverse frame. In seconds, the Schenectady was in two parts. Fuel oil spilled across the harbor, steam lines ruptured. Men scrambled down gangways, staring at a vessel that had, minutes earlier, seemed a triumph of modern engineering. She was 9 weeks old. The damage was so precise it looked deliberate. The rupture extended from the deck edge through the keel, a continuous fracture running clean through 3/4-inch steel plate. The yard superintendent called it an act of God. The Navy called for an inquiry. Local newspapers called it impossible. For months, American shipyards had been launching Liberty ships in record numbers, austere, functional cargo vessels built with welded hulls instead of rivets. They represented a revolution in shipbuilding, faster, cheaper, standardized. Welds replaced thousands of bolts and seams. Labor time fell by half. The Schenectady had been one of those successes, built in 70 days, celebrated as proof that mass production could master the sea. Her sudden fracture threatened that entire premise. 2 years earlier, none of it existed. Not the shipyards, not the production lines, not the workers who built them. In 1941, the United States faced an industrial and strategic vacuum. German U-boats were sinking merchant ships faster than the Allies could replace them. Britain's survival depended on transatlantic convoys, yet shipyards were still organized around craftsman methods, slow, specialized, and incapable of matching wartime attrition. The U.S. Maritime Commission proposed a radical answer: a mass-produced cargo ship that could be built by unskilled labor, using the techniques of modern assembly. The design was adapted from a British prototype, the Empire Liberty, stripped down for efficiency and renamed the EC-2SC1, soon known simply as the Liberty ship. It was basic by every measure: a single screw, triple expansion steam engine, 11-knot top speed, and holds built for bulk cargo rather than specialization. What mattered was that it could be built fast. Henry Kaiser, an industrial contractor with no shipbuilding background, convinced Washington that the same principles that built highways and dams could build ships. He constructed entire yards from scratch: Richmond, California, Portland, Oregon, Vancouver, Washington, each designed for flow rather than craftsmanship. Hull sections were prefabricated inland, trucked to the coast, and welded together on the slipways. It was an industrial choreography measured in hours, not months. By late 1942, the United States was launching Liberty ships faster than U-boats could sink them. Newspaper headlines framed it as a miracle of democracy's production line. The first ship, the Patrick Henry, launched in September 1941 with the promise, "We will deliver the goods." Her descendants would number 2,710 by the war's end. A fleet that carried fuel to the Pacific, food to Europe, and ammunition to every front. But the success concealed fragility. Welding was new to large ships. Riveting, the traditional method, created thousands of overlapping joints that flexed and absorbed stress. Welding replaced that web with long, continuous seams, stronger in theory, but unforgiving if the steel beneath was brittle or the weld introduced locked-in stresses. Wartime urgency forced compromises. Steel mills strained to meet quotas. Workers learned on the job, and inspection regimes could not keep pace with output. The average Liberty ship contained over half a mile of welded seams per hull. Any imperfection in material or cooling could become a stress line under heavy seas. Still, The mood in 1942 was triumphal. Each launch ceremony symbolized industrial power turned outward to war. Women welders, ship fitters, and yard crews, many new to heavy industry, became emblems of the home front effort. The ships were built faster than any had imagined possible. One was famously assembled in under 5 days. They became a floating expression of wartime unity, anonymous, replaceable, and everywhere. No one imagined that the very innovation making them plentiful might also make them fragile. When the Schenectady broke, officials first treated it as an exception. But as production expanded, so did the geography of failure. Cracks off Greenland, fissures in Alaskan ports, fractured decks in the North Atlantic swells. The Liberty program had solved the problem of quantity. The next problem, the one no one had planned for, would come from the material itself. The first reports came quietly, buried in engineering correspondence and shipyard logs. In early 1943, inspectors noted a long crack running from the deck of the SS John P. Gaines, another Liberty ship, down through her side shell. The fracture was welded over and logged as local failure. Weeks later, the same ship split apart in the Aleutian Islands, sinking within minutes and taking 10 men with her. The sea temperature was near freezing. Witnesses said the hull didn't buckle. It simply opened, cleanly, from deck to keel. By spring, similar incidents were appearing in convoy reports from the North Atlantic and Arctic runs. Captains described strange, gunshot-like sounds echoing through the hull in heavy seas, followed by the appearance of sudden fissures across decks or bulkheads. Engineers found hatch corners cracked through, sheer strakes opened, and welded seams fractured in long, straight lines. What unsettled them most was the lack of warning. Riveted ships often groaned and deformed before failure. Welded Liberty ships sometimes gave no sign at all. The U.S. Maritime Commission began compiling data, ship names, temperatures, routes, and types of fracture. The trend was unmistakable. Failures were concentrated in cold waters and on ships that had endured multiple freeze-thaw cycles. Investigators examined welding records and found inconsistencies, uneven cooling, improper electrode types, rapid assembly sequences that trapped stresses within the plate. At the same time, metallurgists from the Naval Research Laboratory warned that the problem might be deeper than workmanship. Some steels, they noted, changed behavior dramatically with temperature. Ductile at one point, brittle just a few degrees lower. The phenomenon did not fit the normal logic of corrosion or fatigue. Cracks often originated not at the surface, but within the plate, where invisible microflaws could grow under residual stress. The term brittle fracture began appearing in reports. It described a failure that propagated almost at the speed of sound across steel that had lost its ability to deform. For every dramatic break like the Schenectady, there were dozens of ships with smaller cracks discovered during inspection, each one a potential starting point for catastrophic failure. Government agencies responded with layered investigations. The Bureau of Ships, the American Bureau of Shipping, and the Maritime Commission formed joint panels to analyze samples. Hull sections were cut from damaged ships and sent to laboratories on both sides of the Atlantic. In Britain, researchers at Cambridge University and the Royal Naval Research Establishment were conducting parallel inquiries, having seen similar fractures in welded tankers. Among them was Dr. Constance Tipper, a metallurgist who would soon play a pivotal role in explaining the phenomenon. By late 1943, engineers understood that the crisis could not be dismissed as local workmanship or sabotage. The statistics were too broad. Over 1,000 ships had reported structural cracking of varying severity. Some required extensive repair, a few were written off entirely. Yet the war demanded that they keep sailing. Crews patched hulls with steel straps, reinforced decks, and continued into the North Atlantic convoys, knowing the flaw remained unresolved. Each new fracture forced the same question. If the welders were competent and the design sound, then what in the steel itself was changing when the ocean turned cold? The search for an answer moved from shipyards to laboratories. Samples from fractured hulls arrived in crates. curved sections of deck plating, jagged and gleaming along the break. Under magnification, the surfaces told a story no human witness had seen. A flat, crystalline landscape where the grain of the metal had separated cleanly as if split by a blade. There was no stretching, no tearing, no evidence of fatigue. The metal had not bent. It had shattered. At Cambridge University, metallurgist Constance Tipper examined one of these samples under controlled tests. Her method was simple but decisive. She cooled small coupons of Liberty ship steel in baths of liquid carbon dioxide, then struck them with a hammer in a pendulum impact machine. At room temperature, the samples bent. At freezing, they broke sharply, snapping with a clear ring. Between those two temperatures lay a boundary, the ductile-to-brittle transition, where the metal's behavior changed from yielding to fracturing without warning. The temperature of that transition for many wartime steels was higher than the seas the ships were sailing in. Her team confirmed what others had begun to suspect. The flaw was not the weld alone, but the steel itself. Wartime production had strained U.S. steel mills to capacity. Under pressure for volume, impurities such as sulfur and phosphorus were tolerated at higher levels, making the grain structure coarse and reducing its toughness at low temperatures. Welding compounded the effect. The heat from the arc altered the metal near the joint, creating a heat-affected zone with different properties than the surrounding plate. In that narrow band, microscopic notches or slag inclusions could serve as fracture origins. When the hull flexed in freezing seas, the crack could start there, and nothing within the welded structure could stop it. Traditional riveted ships had an advantage that engineers had underestimated. Rivet holes and overlapping seams acted as crack-arrestors, interrupting any fracture path before it could travel the full length of the hull. The welded Liberty ships, designed for efficiency, had continuous seams and uniform plates, ideal for rapid construction, disastrous for containing brittle fracture. In effect, the innovation that had made mass production possible had also removed its natural safeguards. By late 1943, Tipper's findings reached Washington and the U.S. Navy's Bureau of Ships. Her reports explained the pattern of failures across the Atlantic and Pacific. Wherever temperatures dropped below roughly -2 degrees Celsius, the risk of brittle fracture increased sharply. The Liberty ships were sailing through that danger zone every winter. Naval architects began incorporating her results into design revisions: rounded hatch corners to diffuse stress, crack-arrestors welded across decklines, and stricter specifications for steel chemistry. The revelation arrived with unsettling clarity. The enemy was physics, not negligence. Steel, under the wrong conditions, could behave like glass. The discovery was both humbling and transformative. It rewrote assumptions about strength, safety, and the invisible boundaries of materials under stress. Understanding the cause did not end the problem. The war still demanded ships, and the factories kept building. The next challenge was to adapt, to repair what was already afloat, and to keep an essential lifeline moving before the ocean claimed more than steel. The Liberty fleet could not be withdrawn. Every vessel carried food, ammunition, or oil essential to the war's survival. So while laboratories confirmed the metallurgical cause, shipyards and naval engineers set about fixing the problem in motion, reinforcing, modifying, and redesigning the very ships that were already sailing through danger. At Bethlehem Steel and the Kaiser yards, engineers began cutting into existing hulls to add crack-arrestors, transverse straps of high-toughness steel welded across deck and side plating. They drilled stop holes at the tips of visible fractures, a simple method to blunt the stress and halt further propagation. Sharp 90-degree hatch corners were replaced with rounded ones to disperse load. Weld sequences were rewritten so that heat would not accumulate in single regions, and inspectors were stationed at every slipway to check cooling patterns and electrode quality. Each repair drew from the growing body of data compiled by the Board of Investigation on Fractures, which by 1944 had documented over 1,000 cracking incidents across the Allied merchant fleet. Material control became equally critical. The War Production Board, responding to tippers and Navy metallurgists' recommendations, issued new steel specifications that limited impurities and required low-temperature impact tests before acceptance. Mills began producing plates with refined grain structures and higher manganese content, improving toughness even in Arctic conditions. These procedural changes slowed production slightly, but restored confidence. Ships once regarded as suspect were reclassified as serviceable. By the end of 1944, new Liberty ships were statistically safer, and older ones were returning from reinforcement programs with fewer recorded cracks. The shift also transformed shipyard culture. Welders, many of them women who had joined the industrial workforce for the first time, were retrained under strict standards. Non-destructive testing, magnetic particle and radiographic inspection, was introduced on a scale never seen before. It created a new profession of inspectors who could detect flaws invisible to the eye. Every arc, every cooling seam became part of a larger system of documentation. Wartime necessity had accelerated the transition from craftsmanship to engineering science. Despite the scale of the crisis, the Liberty program never collapsed. Of the roughly 2,700 ships built, about 1,200 developed cracks of varying severity, and fewer than 30 were lost through complete structural failure. The statistics underscored a paradox. A design judged flawed at the microscopic level still succeeded strategically. Liberty ships continued to deliver 75% of Allied cargo through the worst years of the war. They were imperfect machines that nonetheless kept the global supply chain intact. By 1945, modifications and better steel had stabilized the fleet. The same factories that once celebrated record launch speeds were now measured by reliability. Engineers who had entered the program as builders left it as investigators, having witnessed how small deviations in chemistry could undo thousands of tons of workmanship. The Liberty crisis had become a classroom, one that forged the foundations of modern fracture mechanics and a permanent caution about speed without understanding. When the war ended, the urgency faded, but the lessons did not. What had begun as emergency repair work in shipyards would evolve into a new science, one that followed the cracked plates of wartime ships into every future discipline of structural design. In 1946, the Liberty ships were no longer headlines. Many sat idle in anchorages, their decks rusting under peace. But in laboratories across the United States and Britain, the story of their failure was still unfolding. Not as scandal, but as science. The brittle fractures that had once torn ships apart were now preserved in test samples and diagrams, studied under microscopes that revealed the landscape of broken steel. What wartime engineers had treated as crisis investigation was quietly transforming into a new field of knowledge. At the Naval Research Laboratory in Washington, metallurgist George Irwin began conducting experiments on pre-cracked steel plates, trying to quantify how and when cracks would spread. He introduced the concept of stress intensity, the mathematical measure of force concentrated at a flaw's tip. It was a direct intellectual descendant of the Liberty ship failures, a way to turn catastrophe into calculation. Around the same time, at the University of Illinois, August Fuppel and Alan Griffith's earlier theories on crack propagation were revived and extended, now with empirical data from real-world ship hulls. For the first time, engineers could link microscopic imperfection to macroscopic disaster in a quantifiable way. Industry adopted the lessons quickly. Ship classification societies rewrote their steel toughness standards, requiring Charpy V-notch impact testing at sub-zero temperatures, a method developed after observing how Liberty steel shattered in the cold. Airframe designers borrowed similar ideas for aluminum alloys, ensuring that future aircraft would not suffer the same hidden brittleness. In refineries, pipelines, and nuclear reactors, Fracture toughness testing became a precondition for construction. Each of these innovations traced its lineage back to the wartime laboratories, where engineers had first asked why a welded plate could fail without warning. The Liberty ships themselves entered a second life. Some were converted into training vessels or floating warehouses. Others became test platforms for new coatings, cathodic protection, or welding alloys. The hull of SS Schenectady, the Oregon-built tanker that had famously split in two while tied to its dock, was studied for years, its fracture surface examined like the cross-section of a geological fault. Even decades later, engineers visiting the preserved sections could trace the brittle path of the crack that changed modern engineering. In broader terms, the episode altered the relationship between science and industry. Before the war, metallurgy had been mostly empirical, guided by tradition and experience. After the Liberty failures, it became analytical, ruled by data, temperature curves, and micrographs. The U.S. Navy's Ship Structure Committee, founded in 1946, institutionalized this change by commissioning systematic research on fracture behavior. The committee's reports formed the backbone of fracture mechanics, a discipline that would soon influence bridge design, aerospace, and offshore drilling. For the men and women who had built the Liberty fleet, the revelation was both vindication and reckoning. They had delivered what the war demanded: speed, numbers, tonnage, but at a cost that only science could later explain. The ships that cracked in half had not failed in vain. They had exposed the unseen physics of strength and brittleness, transforming accident into understanding. 2 decades later, when engineers stood beneath the towering hulls of supertankers or traced the fuselage of a jetliner, they did so with instruments and equations born from that wartime emergency. A reminder that progress often begins at the fracture line.